Depeche Mode and Enjoy the Silence. Coming up on my 2020 flood special, one of the effects of Storm Kira was to shave a long time off a transatlantic flight from New York to London. Passengers were carried along at 825 miles an hour thanks to the jet stream. Aviation expert Paul Williams is with me in just a moment to explain how that happened. We've heard about the effect of local communities, the terrible flooding once more, particularly in the Calder Valley. Now, one of the implications of the bad weather and the stormy conditions is a very powerful jet stream. And the storm certainly took passengers on a transatlantic flight from New York by surprise. They must have thought they were on Concorde in some of the moments, because the Boeing 747, believe it or not, reached speeds of 825 miles an hour as it rode a jet stream, which, when I looked, was about 260 miles an hour. That's incredible, because normally these jet aircraft will be travelling about 550 miles an hour. So it was catapulted across the Atlantic, and the 4 hours and 56 minutes that it took is now a new record. So let's talk to Paul Williams. He's a professor of atmospheric science at the University of Reading. He's been on before, a friend of the show. How are you, Paul?
Hello, Paul. I'm pretty good, thanks. How are you?
I'm very well, thank you. Now, this must have excited you just as much as it excited me. Just give us an idea. What exactly happened, and why is this unusual?
Well, it was incredible, really, because not only did it break the previous record of 5 hours, 13 minutes, it knocked 17 minutes off it. And I think I'd been expecting this record to be broken. We have mathematical theories that tell us and describe the equations behind record-breaking events. And what we know is that as time goes on, it should get harder and harder to break a record, because you've effectively got to break all the previous records as well. So this shouldn't be happening. The record's been broken 3 times in the past 5 years. And so that's a sign that something's changing in it. It's not the planes that are changing. They're still flying at about 85% of the speed of sound. And so there's a limit there. It's the atmosphere that's changing. And as you say, this jet stream, 260 miles an hour, quite hard to imagine that, but it's about 4 times as fast as you'd go on a motorway. Really incredible speed.
Now, we'll get onto the physics as to why, and we might explain what the jet stream is and the effect climate change is having. But one of the questions I've got is, would passengers on that aeroplane have noticed that they were going at 825 miles an hour?
Not necessarily, in terms of what they would feel, because, of course, relative to the atmosphere surrounding the plane, they're still going at the ordinary 85% of the speed of sound. So unless the pilots made an announcement, and I'm pretty sure they would have, because they knew the jet stream was going fast and they were about to break a record. In fact, we knew a few days before, because the jet stream forecasts are so good these days. You mentioned turbulence there. There is 3 times as much turbulence in the jet stream than the other parts of the atmosphere. So that's the slight danger with trying to get into the jet stream and get those beneficial tailwinds. There is an increased probability of encountering turbulence, but that's the only thing that the passengers might have noticed, would be the seatbelt sign being on a bit more than normal and a bit more of a choppy ride.
And is that faster than the speed of sound?
Well, this is where it gets a bit interesting and technical. It's all about the speed of the plane relative to the atmosphere around it,
right?
And that was not subsonic.
Yeah.
So when people say that the plane might have been going subsonic, they're talking about its ground speed, but that technically is not what subsonic means. Subsonic is all about the speed of the plane relative to the atmosphere around it. So it gets a bit tricky here to think about exactly what subsonic means when you're in a moving environment.
So if the aeroplane was flying at 825 miles an hour with no help from the jet stream, it would have broken the sound barrier. But because the jet stream is doing 260 miles an hour, the relative speed does not take it past the sound barrier.
That's right. It's a bit like, the moving walkways that you get on airports,
yes,
where you've got your own forward speed, but you jump onto one of those moving walkways, and it propels you forward with its own speed, and so your actual speed relative to the ground around you is given a boost by the moving walkway, propelling you forward faster than you would normally be able to walk.
And I think we've got to spare a thought for passengers travelling from, say, Manchester to New York that presumably had a colossal headwind.
Yes, and flights back in that direction were taking a lot longer than normal. In fact, sometimes, believe it or not, when the jet stream gets that strong. I've known of flights on the westbound route that have taken off with what should have been enough fuel to make it all the way to North America, but they realise that the journey's taken so long because of those headwinds that they haven't got enough fuel in the tank to make it all the way to New York safely. So some planes have had to do an emergency, well, not an emergency landing, but an unscheduled stop in somewhere like Maine just to fill up the tanks and then make their onward journey to New York.
OK, so we've talked about the jet stream. Can you just very briefly, because I'm aware that our listeners, most of them won't really know what the jet stream is, and what causes such high-speed winds?
Well, what drives the jet stream is the temperature difference between the north and the south. So obviously the further north you go, the colder it gets. The further south you go, the warmer it gets. And that temperature difference creates the jet stream, basically, which is a massive current of air, 30 to 40,000 feet above our heads, blowing at speeds that, as we've seen, can get up to 260 miles an hour or more. So
in my head, conceptually, I'm thinking, well, we're living in a warming world, but shouldn't the jet stream become... Why is the temperature gradient, why is the difference between the temperature at the poles and the equator getting stronger? Shouldn't the whole planet be warming? Is it because the Arctic's warming at a different speed to the equator? Why is the jet stream becoming more powerful?
Yes, that's a great question, and part of it is the Arctic warming, but that doesn't go very high into the atmosphere. By the time you get up to 30 to 40,000 feet, it's actually the tropics and the equator that are warming the most rapidly at those altitudes.
Right.
And that's because basically, as the planet gets warmer, there's more water vapor in the atmosphere, and as that rises and condenses, it releases what we call latent heat or just hidden heat, and that warms the air parcel in it, and so there's a little feedback there, so that we see amplified warming in the tropical part of the planet. So that's warming more rapidly than the Arctic at high altitude.
So on the south side of the jet stream, at the level where the jet stream is created, it's warming more quickly.
Yes.
But so that's what I didn't get my head around, because the Arctic, as we know, is the fastest warming part of the planet at low levels, but
ground level.
Aloft, that's not the case.
That's right. In fact, it switches sign, and the whole effect becomes the opposite way around when you get those. So it's a messy picture, really. Right.
Well, that's really interesting. That's put my, because at times I'm thinking, I can't fathom this out, but now you've answered that question, so that's fantastic. So let's move on to the next step. Climate change, without doubt, the evidence is all around us. The projections are all in line for a warming planet. What does that mean for the jet stream, and what does that make for transatlantic aviation?
Well, it's increasing something called the wind shear, and this is just the effect whereby the higher up you go in the atmosphere, the windier it gets. That's what meteorologists call wind shear. And in a study we published just a few months ago, we looked back over the satellite record. So we went back to the 1970s, which is when the satellites first started measuring the jet stream. And by looking at those observations, we found that it's become 15% more sheared than it was when satellites began observing it. And unfortunately, it's shear that generates turbulence. So this is all consistent with the jet stream potentially speeding up, but certainly getting a lot more turbulent at those high altitudes.
That's really interesting, because I flew back a week ago, and the pilot flew at 42,000 feet, and he said he was trying to get out of the turbulence as a direct result of the jet stream. And that's very high, isn't it, for a jumbo jet, 42,000 feet?
Yes, they can't go much higher than that.
No.
Yeah.
But I tell you what, that's fascinating. You and I will be able to sit down the pub on a Friday night and talk about, I think there's something, a friend of mine's a pilot, and whenever we get together, the combination of aviation and weather and climate, it's just, we're two of the same things, aren't we? So maybe next time I'm down in Reading, we'll go for a pint and we can talk further.
I look forward to that, Paul. That'd be great.
That's fantastic. That's Dr. Paul Williams, Professor of Atmospheric Science at the University of Reading.